So I'm not going to go too much through code. There's code here that's published that there's a link to in the reading in the folder for IMU and ACC. I'm mostly going to go through how they could help us resolve behavior and add to those points in space. So if we wanted to understand what an animal was doing as it was moving through space, the clearest thing would be to stick something that we can sense easily. So you're going to put some camera on there and fully immerse yourself in the animal's world and try and understand what it's doing. You could be looking at the tail movements here, that it's got a body angle, that all of that relates to its flight performance. Whereas a video on the back of this penguin is showing the diving behavior, what is in its environment. In a second, there'll be some fish that it's about to hunt on, and then there's other individuals that also it will be interacting with. That's really power hungry, and most of you won't have cameras. You might have camera traps, but probably not on the animal itself. Power hungry and very heavy. So we use other sensors that essentially allow us to visualize, play back the behavior in the same way that a video would, but this time it's signals. So here we have, I'm going to go through them, but we have an accelerometer that's telling me that this bird is basically doing nothing for a really long period of time, and then it's flapping consistently. I have a pressure sensor that when you calculate altitude from that is telling me when they are rising and using soaring because they're not flapping whilst they're rising, and when they're gliding. And in this case, they glide down to the floor because they're flapping too much. And then this is a magnetometer, which is a compass sensor, which many tags now have if you are saying, I want acceleration. The chips are coming together more often, and you'll have a 9-axis IMU, but there'll be, I think most people in this room that are using acceleration probably don't have a magnetometer with them at the moment. And that tells you position relative to north. So here in this case, we've got a sine wave that's going back and forth, and I know from that video that that's a turning behavior. It corresponds to them gaining altitude, and they're not flying. So this is cheap flight, and this is expensive dropping flight. So if I was to watch that play out, all of those squiggles, my eyes are doing this, like working out a video of what the animal's doing. And then you can start to classify behavior from that and add that to your tracks. So we're going to go through that process. With all of this extra information, then, we can gain, there's lots of models that you're going to go through as to why an animal did what it did. But there's an argument to say that you can gain more in-depth mechanistic understanding of animal decisions or movement decisions if you have these auxiliary sensors. You can also start to tell you about the internal state of the animal. So if it responded to the environment in a certain way, that might be because on this day it is spending more energy overall. Or you could have other auxiliary sensors that I haven't mentioned yet, like heart rate, and some physiological sensors as well that will tell you about their internal state. Intraspecific interactions also come up quite a lot, and that's where my focus is, so I'm going to come back onto that later. And that could be how they respond to the environment, but also by piecing together auxiliary sensors of multiple individuals at the same time. And then we can reconstruct fine-scale movements. So instead of saying that we have a GPS every hour, every minute, maybe every second, you can also say that we have sub-second resolution of how the animal traversed the landscape and how it made its decisions on a step-by-step basis, where it's actually a step, even though we were talking the other day about it not being a step. But there's challenges with that, and we're going to go through that as well. Where the different sensors are providing you a little window into one aspect of movement, and you need to be able to put them together with many sensors to actually get a full picture of their behavior. And that is full of complex analysis, especially when we're working at sub-second levels that we might not be used to with our models, for example. And yeah, it gives you approximate cause of the behavior, but then relating this very fine scale data up to a bigger ecological picture, maybe evolutionary, on how they're making these decisions or why they're going where they go, that's another step. We're getting a very fine window into their behavior with these sensors. So this is an example of a biologger that is, in this case, it's a daily diary from Swansea University, and it has a SD card, and it's a logger that is purely archival, and then you have to go and pick it up afterwards. So on this logger, we have an accelerometer, a magnetometer, and sometimes a gyroscope, and that would be housed here. And then we have multiple other sensors at the same time going on that include pressure sensors, temperature, light levels sometimes, and then we have GPS. And the power of these tags is being spent on these auxiliary sensors, and very often GPS is at a much coarser scale, because it would be very, very expensive to increase that to sub-second level, for example, and probably pointless with error. And it's these three that make up the inertial measurement unit. So it's a 9-axis unit that is sensitive to 3 different planes. As we'll go forward, actually, I'll jump. 3 different planes of the, 2 planes, sorry, 3 axes of the animal's frame of reference. So we have surge, heave, and sway. And all 3 sensors are sensitive to this, but not aligned in this way. So they're orthogonally, they have 3 axes that are orthogonally positioned, orientated, and then they all have a different frame of reference, and you can put them all together to get all the movement of the animal. So we get these 3 axes, and then we can put them together to calculate pitch, roll, and yaw. And these are what tell us the behavior of the animal, is the sequence of how they move in the posture of pitch, roll, and yaw, as well as active movement in surge, heave, and sway. So I'm going to go through these IMU sensors, but just first I'll jump back to here. So these 2 GitHub repositories, I'm going to go through the code from these 2. They're both published and freely available, and they have examples in there as well. And I'll put screenshots of the code as I talk about different aspects of it. But if you want to go through it, then this information is in the folder that you have, and you can go to the GitHub now and open the code that I'm talking about as we go through. So the accelerometer, which most people have. The way that this is working is it's a sensor that's sensitive to gravity, and it has essentially a spring in there. That's not the case, but at one point it was. and that spring has 3 of them, if you will, aligned to that surge, heave, and sway axes. If the orientation of that changes relative to gravity, then you get a measure that tells you about the angle of the posture in that orientation, in that axis, sorry. But the spring also, if you were to run up and down or jump up and down, then it creates its own acceleration and force relative to gravity, which is picked up, and then that makes it spike. So everything to do with posture relates to the gravity that we experience all the time, so it's 1g, and everything related to activity is an increase in that gravitational force, really. How you are moving, it's an increase on the sensor. So this is an example of an acceleration output. It has this nice background smoothed signal, and that tells me about the posture of the animal. So if you imagine that spring in the heave, so that's the vertical axis of the animal, as that vertical axis moves away from the vertical, you get these peaks. So this is the animal kind of bending down, bending down, bending down, and that carries on. You see all of these patterns. If that was to go the other way, then that would just mean that it was bending backwards, as it was to go towards 0, but in the other direction. what we do with this information is first smooth it to take out that postural information. Many of you will have, well, the people that put their hands up will have raw acceleration data that is some arbitrary number that you need to then convert into G. When you convert it into G, you get numbers that are between 0 and 1. When you then smooth it, you're taking out that one gravitational unit, and it tells you about the posture in relation to pitch, roll, or yaw. So now you've got the movement instead of the axes themselves. What is then left over becomes the dynamic signal, is that spring that's moving up and down. So here, there's very little movement going on in this dynamic, the noise around this smoothed signal. And that's because it's on a vulture, and the vulture is doing a little bit of walking, but it's not really putting in much force to do any active movement. Then see these peaks where it's bending down. But again, we're still not seeing much noise in the residual, the dynamic that's left. And these peaks are related to the angle at which they're bending. So here they're actually reaching the floor, and then they're coming back to standing up. And that's because the bird is now drinking. And then the final bit of this little bit of behavior, the bird is again doing these bends, but now you see these big peaks in the dynamic signal that's left over. And that's because the animal is now feeding and pulling on a carcass. And interestingly, you can calibrate this system so that then the size of the peak, the amplitude, and the duration of the peak tells you about how much food they would be pulling at that time. You can get pecking rate, for example, and also relate it to the amount of food they could be taking when it's well calibrated. So I would use those signals in the smoothed and in the dynamic that's left to inform us about the behavior that they're doing. You could use classification systems, which we'll come back to later, to be able to categorize these into nice, clean behaviors. And I've kind of alluded to it already, but the accelerometer it's mostly used for energy expenditure, and it's because it's a proxy for oxygen consumption. So most people will use VEDBA. You've probably heard of dBA already. And that is the total sum of that noise that we saw in the previous slide. If that total sum is high, then it's a really energetic behavior, like this jumping gazelle. If it's really low, then it's still behavior. It's just that the animal might be at rest. So the accelerometer can tell you a lot about the explosiveness of that behavior that you could then add to your GPS tracks. There's a lot of processes that we have to consider as we take this dynamic signal out of the accelerometer. The most important one is the sampling rate of your sensor compared to the rate at which the animal's behavior is performed. So if I was interested in flapping, I would want at least 4 points, for example, per flap of the bird. So my flapping rate is 2 flaps per second. So I want to have, well, they say at least twice, but I like 4 because then you get a nice peak. But the absolute minimum you need is twice that in terms of frequency. Otherwise, you will not capture that behavior. And also your dynamic VEDBA or whatever measure you use for the dynamic acceleration also won't actually be comparable. You will miss these big peaks. The other aspect that you need to fully understand is your sensor resolution and the range of the sensors. Often people are putting accelerometers out that flatline at a certain amount of force. So if you see a flapping bird or a walking bird, you could get what seems to be a flap, and then it flatlines, and you never know what actually happened or what the actual extent of that behavior was, how dynamic it was, or if it's a different gait to another behavior. And that's also related to the sensor resolution, depending on how the bit is arranged, how it's separated out. All of that's kind of more important if you look trying to separate out behaviors and get this smooth signal away from the dynamic signal. It's by smoothing the data that you see this postural change. And this is another aspect that you need to be really careful with, is the smoothing window of the accelerometer and how you extract this signal, because it's what's left that's going to tell you about the dynamic signal. If you don't remove that, then say you only have a 2-axis accelerometer, you don't know how to partition the gravitational force of you just stood there but at a different angle in that axis, or you actually moving in that axis. And then we use our validation. That could be to do with if you've got a calibration, a camera set up, examining their behavior at the same time, and you can put those things on to overlap them together, where you've got your signal playing at the same time as your camera. That really helps you validate the behavior. You don't actually really need it. You can follow the signal through. But sometimes things happen that are really strange, and validations really help. So if you've got an animal in a mountainous environment, all of these sensors now change because the animal's plane is now uphill. So it's not parallel to gravity anymore. So all of your outputs now have got a different value. And you need to be able to correct for that change. So I'm putting a few slides up like this as for kind of future reference, that if you start to explore the accelerometer more, or any of these sensors, just to go back and do checks with, do you know this information and can you account for that? This is the sort of data that, this is the data that I collect, and some people in the room will have this sort of data. So often you have a GPS that comes on, gets one position per however long, whatever your rate is. So in mine it was 1 second. I've got a GPS at this second, and when that switches on and it gets a timestamp, it then also collects 40 values for acceleration, magnetometry, and GPS. So I have essentially a 40 hertz behavior or sequence that will tell me about behavior, and I can also then resolve the tracks to 40 hertz as well. But the other setup that some of you may have in the room is where, again, it's triggered by GPS, but the way that the device records these auxiliary sensors is just putting them one after the other within the same cell. There's different code available to be able to change this and that into time series. And I believe that not Move Apps is doing this, but Move 2 has that in there, right? Does Move 2 have the code to be able to transform these EOBS tags into time series? Otherwise, it's simple code. That you've got like X, Y, Z, X, Y, Z, X, Y, Z going through.
This little R package that I did many years ago, and that is still on GitHub and kind of surviving and working.
It's in there.
That does that for EOBS. So for all EOBS, or for the ones that have the structure of EOBS, it can separate those things. So it's done for EOBS. So you have to tweak the code to maybe adjust it to other. But this is EOBS. So this would work for EOBS, and it will be updated at some point.
But so the reason why it's stored like this is because MoveBank stores it in one variable. So because of the definition, we don't know how many sensors there are. So this is acceleration, and therefore you don't know whether it's 2 axis, 1 axis, or 3 axis acceleration, because you can actually also choose not to collect all 3 axes, and at which frequency, and so on and so forth. Therefore, on MoveBank, there is one variable that contains the acceleration data, and you have to know what is in it.
And I assume then that the study's description will tell you everything about the frequency at which it was collected.
No, the study description doesn't tell you, because you can actually also change that. So I can collect one day 1 axis at certain resolution, and then next day I figure out now it's actually not enough resolution, not enough data, and then I switch my tag to something else. So MoveBank doesn't know about this. You have to know about this. I have also spent some time to reverse engineer what people were thinking in their heads.
But that this column of frequency should always be there. Yeah. So then it means that there's, in this case, there should be 10 values per row, and there's 30. Well, there's actually 33 per row in this case, and this is the example data that's also in the folder.
But also as a word of warning, if you actually compare the sampling frequency and the number of points that measurements that you get, sometimes it doesn't work. So sometimes you have fewer measurements than the frequency suggests. Sometimes you have one more.
All depends on how long it takes to get its GPS fix and then to initiate the turn on of the accelerometer. And sometimes how long it takes to record it to the memory. But yeah, this is the data that you have for the stalk that you had at the beginning of the week. It also has acceleration for that individual. And so you can go through the move bank code that you learned on Monday to be able to download the acceleration data if you change the sensor ID. And this is what you would be faced with. And so then it's about using some code to bring this column into a time series of multiple rows, in this way 10 rows per second, or per GPS. So as well as being able to just generally say what they're doing, and then we'll get onto the classification later to specifically say what they're doing, we can create these metrics for energy expenditure or for overall activity, or they would also be related to behavior. So in this case, I have a flapping bird again, and this is the dynamic signal, so it's the residual of that smoothing. And each of these peaks corresponds to a flap. There's a code also in that folder that allows you to pick out the peaks themselves, and you can take different metrics from that, just like peak frequency, amplitude, overall time spent at a certain threshold to get flapping behavior. And you could do this with running, with swimming, anything that's an active behavior, then you get all of these peaks, and usually we're finding some descriptive metrics to bring them together. But you can take this and get that area under the curve, and that is a DBA, a dynamic body acceleration. And there's been many studies that have shown that this has a relationship with oxygen consumption. And it's for that reason that we can then use these metrics of DBA to tell us about energy. The important thing to note is that it's relative, and we'll come back to some of the challenges for each animal. You can't compare absolute VEDBA and ODBA values between individuals because the tag will move in loads of different ways specific to that individual. It's not a value that is actually energy expenditure, and it's not a value that's comparable. These two repositories have code to be able to take out these peaks, so I just wanted to highlight that there. And then you can take the area under the curve to calculate the VEDBA, which is this dynamic body acceleration. So this is the code that's in your folder. It's very simple, and this is why we're not going through it ourselves. It's a very, all you have to do is smooth the signal. In this case, we're using a running mean, and then we take these three, and we'll come back in a sec to how we sum those three axes. So the dynamic body acceleration, you have these two measures, ODBA and VEDBA. ODBA is the sum, and VEDBA is the vectorial sum. There's different behaviors that these are sensitive to. If you're really interested in the energy expenditure of the animal, the ODBA tells you more about like the opposing muscle movement and how that relates to energy expenditure, whereas VEDBA is really just the whole activity of the animal, takes out all of the axes, and is just like, this is a nice active measure, but it's less related to oxygen consumption because it's not really thinking of the opposing muscles that are both at work to do any movement. If there's any questions about that, we can come back to it. But because of the use of VEDBA and ODBA and how they're all kind of related anyway, then it's now a new field, a new school of thought is coming out that is just use DBA, the dynamic body acceleration, and don't try and sum them with this vector or just absolute values. Yeah, so I encourage you to go read this paper if you're really interested in why you would want to use oddbert, vedbert, or dBA, but they all relate to each other. And this is the simple code to be able, well, it's just maths, to be able to get the square root of the squared dynamic acceleration signal in each of the 3 axes, and that gives you the measure of activity. I've already mentioned some of the factors that would affect dBA metrics and why you can't compare individual activity with just an absolute measure of dBA. Because the way that we attach the tag to the animal, you can get a lot of movement of the tag itself, which is not related to the animal's movement or expenditure. You get a difference with tag position as to whether it's in, say you put it on the end of the wing, you've got a completely different measure to if you put it on the body, or if you put it on the leg and it starts walking around. You've got to be aware of the sensitivity of where you've attached it to the behaviors you're interested in. The environmental dBA, so if you imagine that albatross, if it had a accelerometer on it whilst it was going into the eye of a storm, the storm would likely also affect the amount of movement of that tag, and it would come out to you as an active behavior when it might have actually been the environment causing that. This relationship between oxygen and dBA, it's a different relationship depending on the biology of the animal. There's a lot of laboratory experiments with different bird species and mammal species that are using doubly labeled water or different methods to get oxygen and then relating it to dBA. And you can usually find something that is related to your species in some way, but obviously that's not natural, and it's also often not your exact species. So you have to understand that this is a proxy for energy expenditure and for VO2. We also have pulling G. My birds do this a lot, and it can affect how you say how expensive is one behavior compared to another. If the bird or any animal does some rapid change in velocity, say you're on a roller coaster and you go over the top of that roller coaster, you feel really light, and that's because you actually have, you weigh less in that moment. There's less gravity acting on you, and so the sensor also doesn't pick up as much gravity. So its outputs are all of a sudden all lower. You also get problems in free fall where an animal, like a bird, would just, I can see some questions coming up now. No, sorry. If the animal was to fall off something or, free fall, then all of a sudden you weigh 0 and you have 0 G acting on you, and so also the accelerometer won't work in that instance. And when my birds are thermaling, it's constantly turning, so it's got a centripetal force on it, so the accelerometer doesn't tell me anything in that moment of time either. All of these issues are why we might use a different sensor to tell us about behavior, and that's where the magnetometer comes in. So the magnetometer is exactly the same as the accelerometer in that it is sensitive to these 3 axes and 2 planes of movement, but it has a different origin, or the sensitivity is to the north, the magnetic north pole, and because of that, it's no longer in a parallel with what we is usually our operational plane. So usually our plane is gravity, and you're on the horizontal plane, and everything that's sensitive to it means you can get these nice pitch and roll movements. What you can't get from an accelerometer is yaw, because if I face this way, I've got the same amount of gravity acting on me as if I face this way. So you get no directional information from an accelerometer. The magnetometer, being sensitive to the magnetic north, puts it on an angle, and wherever you are in the world, it's a different angle. So when you're at the equator, it's basically perpendicular to the accelerometer, and when you're at the North Pole, it's in line with the accelerometer. Because of that being off, you can now get orientation information, and that's how your compass works. So when you face magnetic north, it reads out a maximum, and when you face magnetic south, it reads out a minimum. And that allows us to see those nice peaks that I showed you at the very beginning. So if I have here an accelerometer and a magnetometer on a soaring bird, all of this noise we now know as the dynamic signal. It's arguable that this could be the environment that's causing this noisy signal as the wind is affecting the feathers and the way that it's attached to, the tag is attached to the animal. When you see it in the 3 axis of the magnetometer, you see less noise, but you also see these nice peaks, and that's as it faces north, south, north, south, north, south. So the animal is turning. And there's a lot of, actually, it was brought up earlier in the week of just how much animals turn and go through different rotations that is a notable behavior. So you can use the magnetometer to get at that information because it's sensitive to orientation, to north. And the same is true when it's attached to this whale shark, that the whale shark has some movement in its sway axis as it's moving its tail, but the translocation is happening across axes. And that's to do with it being a passive behavior that's not being picked up by this active sensor that is the accelerometer. So whenever I put a tag out, and whenever anybody in the future puts tag out with IMU, I urge you to do a lot of calibrations. So every time I'm in the field, I'm doing a dance that I know by heart. It's a great dance. I ask all of my subjects to do it because they're people. They can do my calibration dances for me. So I have a calibration protocol then that tells me about which axis is which within the side of the tag. How does that relate to the animal's frame of reference and its movement? And then I use this information and put it into the code that I highlighted before. So if you go through that code, this is what it's doing. It's finding your heave, surge, sway in the acceleration. So here you see a lot of blue peaks, and that's because I went like this with the tag. And then you see a lot of red peaks, and that's because I went like that. And then the black peaks are because I've gone like that. So I've activated it in 3 different axes. But the mag does nothing, and that's because it's only translocational movement, and it's not angular movement, so it's not picked up. Here, again, there's no output in the accelerometer. It's stayed static in posture, but it's rotated only in yaw. So you see it coming through here in the magnetometer and not in the accelerometer. So if I was to look at behavior and classify it from acceleration alone, there's things you can't say, and the main one being rotating on the spot as a behavior. And then all of these correspond to different movement types that then allow me to calibrate my sensors afterwards. The magnetometer is very sensitive to other forms of magnetic material. And so we have to do corrections with our outputs to account for soft iron and hard iron that's either globally distributed or, say, on a volcanic island, all of a sudden your magnetometer is not very useful anymore. And that's also in this code. So this is what I do when I get data back. I take my accelerometer and magnetometer, put them through this Gundog compass code that does the corrections for us, bringing the hard and soft ions back onto a 0-0 origin, so that then you can plot the 3D data on a sphere where everything sits on the sphere, and the point tells you the orientation in 3D space on that sphere. I can then take both the accelerometer and the mag to calculate pitch, roll, and yaw, knowing that I've now captured this yaw element. And it's using this data that I then do my behavioral classifications. So we can then understand not only what the animal did, but what orientation it was in when it did it. So for example, with vigilance behavior, this animal relates to what Martina was saying earlier on in the week. If you've got a GPS heading, it doesn't necessarily mean that the animal is facing that way. Especially if it's an animal in 3D space, it could be facing another orientation, completely interested in something that you have not accounted for because you assume that it's going in this direction and therefore is looking in that direction. This animal, I don't have its GPS here, but however it was orientated for its direction of movement, this is the direction that its head was facing because we put the tag on the head of the animal. And now we're starting to see, well, where in the world was this individual interested in? I also use it then for performance metrics. Instead of using dBA, we can use the magnetometer to tell us how, what was the body angle of the animal when it was doing certain movements, and that relates to performance in the terms of flight. And then with the albatross, again, another thing that would align with the wind is how their behavior as they do one of these nice dives to pick up speed and lift from the wind, they do this repeatedly, and the coverage on the sphere is telling me the overall pattern of motion. If that's on top of each other all the time, then you know that there's a consistent individual behavior that they're doing. If over time that also changes, then it could tell you something about how they're learning to perform better, hopefully. And again, there's lots of warnings with the magnetometer as well. But altogether, it's the use of the two that make up this IMU. There's gyroscope as well, but I'm not going to go into that. That's not on many tags because it's very power hungry. So using the accelerometer and or magnetometer, we could go through these steps to then get to this behavioral classification. So here I have 4 behaviors from one of my vultures, and I've used the mag, accelerometer, and the pressure to tell me about its behavior. There's no positional information here. There's altitude, I guess. And there's very easy ways to be able to identify behavior without going too complicated into machine learning. And with acceleration that a lot of you have, if you calculate VEDBER or ODBER, you can use a threshold to say it's this behavior. That's the simplest way to be able to classify behavior from an accelerometer. So all of 3 cases have very little acceleration signal, but flapping is a very stereotyped behavior. If I was to calculate a VEDBER threshold on that, it would be very high compared to the other 3 behaviors. And then I can also calculate thresholds on the magnetometer as well. So a lot of IMU studies will use a decision tree to get at behaviors and classify them into discrete behaviors this way. Otherwise, you would use a continuous measure of VEDBER, for example, to tell you about energy expenditure. There are other ways in which we could classify behavior from an accelerometer. I'm not going through these. It's the same technique as other models that you'll be learning this week, and statistical methods as well, but you can put it into any of these things. And it's a way of visualizing your data, taking this and putting it within a Boolean-based system that is flexible. So for example, here, if this was a rotation of the animal going north-south, and maybe it did something on its way, you would say it can take as long as it wants to rotate through north, and as long as it wants to rotate through south, but these things have to occur within a certain time frame of each other. And so then it's running a machine learning algorithm to be able to capture the flexibility of the behavior from these signals, and then classify it based on that. And I just wanted to go through a little example. So even if we're not going through everybody's data next week with IMU, this is how I use it myself. So here I have a condor that has a GPS tag here that will stay on forever, and then it's got a logger, the daily diary, that's collecting all of these acceleration and magnetometry and pressure data, and then this drops off after 2 weeks because it's a very demanding power consumption and it can't recharge itself. So it drops off, we get it, and then this is all the data that we get back. Again, you already know all these. We have a rough GPS, as in every 15 minutes. So I say rough because I'm used to once per second. And then we can label the behavior using the accelerometer or turning angles, as we discussed earlier in the week. And then we can also do this thing that's dead reckoning. So here, I have GPS every 15 minutes, and that's the black dots. And when we were talking about interpolation earlier in the week, you have no idea what the animal did between those two dots. If you use the magnetometer and accelerometer to tell you the angles and relate it to speed of motion, of movement, you can piece together the track by a process of dead reckoning. That is what ships used to do and still do. That says, I travelled in this direction for so long at certain speed, therefore my next point is somewhere else, and you can piece it together. So here I have a vulture that is soaring. It's got 3 GPS points. I would never have known that it was soaring from that GPS alone. You put on the dead reckoning process, and now you've got these nice rotations in space, and you know for sure that it was soaring. So the process of dead reckoning to try and interpolate your points to add detail to your track. I will go through it quite quickly because it requires high frequency IMU data, which many won't have. So we, instead of using, well, DBA being a proxy for energy expenditure, it's also a proxy for speed. And you can imagine that usually speed of movement requires more input or a more explosive gate or a higher frequency in your gate. That then means the sum of your DBA is also related to speed. It's not always the case. There's a lot of caveats with that, especially for a passive moving animal. And then if you're in wind, that also affects your speed, obviously, if the environment's moving. But because of some proxy of speed with DBA, or with these peaks that you get with every wing beat or with every step, you can use the ACC to tell you how far it went within a certain time, and use the ACC and MAG to tell you in which orientation it was in during that time, and piece that together to expand on your tracks and tell you the story of how it moved. Again, the information for that is on the code, but this is what it's doing. It's taking, this is a lion, and it's taking all of these GPS tracks that we have in black, but now it's putting on the acceleration and magnetometry and telling you where it actually went at a much higher frequency. And that's the process by which it happens. We use the MAG to get the rotations, this yaw value relative to north. We then have to put it onto Earth by accounting for the pitch and roll in the acceleration. We add our speed metric to it, which is either flapping frequency or DBA, convert that to distance, and then recompute our new positions between GPS. But you can also use it to correct your GPS. Knowing about all of the errors that we have in GPS, you can work between the two processes of GPS and dead reckoning to verify your positions. And the process for doing that is also in the slides, but I won't go through that now. So these are our informed tracks with acceleration and magnetometry. And I want to focus in on this one of another bird again. And here we have the bird climbing. We had some GPS points in there, only 3 per climb and drop. But now we know the very fine scale and accurate track of what it did. And the time is a bit of a wiggly line, but yes, it's going in my flight from, I don't know the time actually on that. And we can say a lot about how expensive it was in those different periods of flight, and how it made its decisions a very fine scale precision. The other argument here, to be able to say that it is actually an accurate track, is to use a barometric pressure sensor, because the sensitivity of a barometric pressure sensor, once you've accounted for sea level pressure, which we can get from a lot of weather stations, local weather stations, is far more accurate than the GPS altitude. And so there's a few different papers out there that would give you an argument for why to use a barometric pressure sensor instead of the GPS altitude. And piece that together as another auxiliary sensor, and then we have a nice accurate track and behavior. So that's it for the detail of IMUs. I realize that it's might not be fully related to what everybody's doing at the moment, but now you can see the power of it for future research, but also for those that do have them. They're very powerful and you can really dig into them. There's obviously then an added complication of how we bring together different sensors. What is our question and how is that related to the sensors you have? When you have multiple in a biologger or however you're collecting your data, you become quite lost as to what is affecting what's the cause and consequence of your behavior. And you need to be a lot more specific with your question and hypotheses. And so there's different ways in which we might attempt that, bringing together different expertise along the way. And so it's just a bit of a word of warning for understanding the biological relevance of these sensor outputs and how you address a question. And a lot of us will put out these IMU sensors to see what we get without having a question and then trying to figure it out afterwards. And there's a lot of words of warning in all of those slides that would maybe say do it the other way and do a question-driven instead of data-driven approach. And that's it, actually. That's the last slide. So a bit more about fine-scale behavior. Okay.
This was absolutely fantastic, just incredible. I
don't want it to be lost. I
didn't definitely understand everything, but it was amazing. And I just wanted to ask you, very basic, if you could talk a little bit more about the device, the diary. How, like, you put it on the bird and you need to retrieve it. How do you retrieve it from the bulge, or does it shed it, or do you recapture the bulge, or?
No, we just capture the tag. We use one tag to tell us about the position of the other tag. So if you have the less frequent GPS data, you can use that to tell you where a more frequent sensor with data logger is. Here we've now moved to send data back to us. So here we have a wildfire tag that sends data via Wi-Fi back to us here. So that was one example, but they all work in different ways. The biggest thing and the limitation as to why many in the room won't have ACC or IMU is because of power and memory. And so you have different methods of getting around that.
And these devices I saw on the GitHub, these are also open sourced and built in-house?
More and more so open source, but many of them are not. And you still buy them, and they can be very bespoke to a species. But there are some out there now, like the EOBS logger that I showed you, that does ACC on many of its tags, the bigger animals especially, the bigger tags. But is still working towards making it more complex to
really
match
cool.
the bespoke ones.
Thank you. This is really cool.
Who's the chair?
So yeah, great stuff. I'm just kind of practically, you get accelerometer data from, let's say a month of tracking data. How much, and you need to classify it, right? So I guess you have some validation data already, or do you use validation data from other birds to classify it? And like, how much time does it take, and how much of the data do you need to validate? How many, those kind of practical questions. Because we have accelerometers out, and we're going to have to classify them. And, we haven't done that yet, ever. So I'm just really curious. Thanks.
Yeah. So I'm in a weird situation, I think, where I've only ever known really high frequency 3-axis accelerometers that are continuous in their recording. With that information, I find it, once you immerse yourself, you can really see the animal moving. And the validation is, it's frustratingly required, but to publish or to prove or whatever. But when you're looking at it, it's just like watching a video. As soon as you then start pulling away data and you say it's burst and we don't have the whole time series, you don't know the story of the motion, maybe you only have 2 axis, or maybe you already have onboard processing of that data, it's harder to see it in action and to understand why it actually happens. So then the validation is 1, more important, and 2, more time consuming, because it's harder to see the picture at which it occurs. You don't fully know what the animal is doing at any one point, so you have to have some video data. The good thing is, and Cameron's going to say something, the good thing is that you can't defy the physics. So the accelerometer, it's not giving you, how would you say? I'm trying to think now. It's a very accurate sensor. The misinterpretation of the accelerometer is harder to do. If you see those peaks, you know that it's flapping. What else is the bird doing? So some things are just very clear. But the more nuanced behavior, then it requires a lot of time, especially if it's not doing it very often and you need to film it every time it does it.
So, well, Ellie, can I ask you, do you have bursted data? So you're collecting 5 minutes and then
I'm
pause?
not 100% sure what the...
You have no idea?
I don't know offhand what the... it's not continuous, but there's also still going to be too much of it. I mean, for us to look at. So it sounds like what you do is you just look at that thing and then you go, okay, this is started doing this, it started doing that, it started doing this, it started doing that. Right? For the classification, you're manually classifying in the end?
Yes, in the past, yes. And a new project, new species, new tag, yes. But then after that, these thresholds, relative thresholds, I do a lot of standardization. So I center my VEDBA, and once I've created pitch, roll, and yaw, then I'm also looking at rate of change of pitch, roll, and yaw, because that's much more comparable between individuals and species and tag types. So then I can use this Boolean-based machine learning on more nuanced behavior. But yeah, to start with, you need an understanding of how your animal's moving and what the outputs, what reflects what. Yeah.
So I don't know whether you remember on Sunday, I was talking about Julia, who did the behavior classification of golden eagles. So like feeding, flapping, roosting, and so on. So in that sense, that was EOPS, that's bursted data. So we get 8 seconds of 33 hertz ACC data. And so what she did was she went into a falconry, took golden eagles, video cameras, and put tags on birds and made them do specific behaviors that were documented on video. And with that, she did kind of an classification algorithm that would classify the behavior. She also then went to the field with a clock that was synchronized to the schedule of the tags. So she knew that now is a burst. we figured a couple of things out then. So internet time and GPS time are off by 18 seconds. You would think that it's the same, but it isn't. GPS time is off the world time. But once you know that, you can actually observe the animal while the ACC sensor is working. So she did field observations for the rare behaviors or the behaviors that you don't get the animal to do. I think in the long run, what we probably are going towards is either a library of behaviors that people have data streams for, and or I've been talking to people from image processing. So these are the people who are actually doing movies that have no people in it. So they actually reconstruct fake videos they make actually. So it's the same data input. They can actually make a bird based on the data stream that behaves. If they have a mechanistic model of the bird, given that data, they can exactly reconstruct it. For them, it's interesting questions like how many sensors do we need? Is one on the back enough? Because you can imagine that these inputs are vastly different. If you put a sensor on the tail of a bird or on the head of the bird, a lot of the birds have their heads as a gyro in itself, so the body moves. There's great videos of a pelican with a camera on its head. The camera is steady as shit. The body does all sorts of things in the back because birds keep the heads straight. If you take a chicken, you can turn it around, the head will always look at you. It was a Mercedes advertisement, so it really depends on where you put it, and that's why also you can't compare between individuals. So how slack or loose the tag is will actually affect. Also kind of in the wind, the turbulence behind the back of the bird will create different amount of dBA. So I think for that sense, once you have calibrated it, flapping, non-flapping is like 100% accuracy done in no time. So I guess even if you have continuous data, you will want to bin it somehow. And then I trained as a behavioral biologist, so then interesting questions come up. How long does a behavior have to be before you recognize it as a behavior? So is 2 minutes of scratching, or is it a short scratch? So yeah, behavior is always our classifications. It's not like they have a concept of I'm going to do this now, and this is very different from that.
Yes, we have actually collars with both accelerometer and magnetometer on the lions, and we are really struggling with this validation, especially if you don't. These are animals that, sleeping, I can validate sleeping for a long, long time, but it's very hard to pick them the moment that they do a hunt. We are not in a population with a lot. We are really struggling with that. And also I wanted to actually ask you a question about the collar cannot be probably as steady as on a bird because you need to leave always some space. So there is the risk that while they roll, they sleep, other things, they turn.
Yeah.
And from my understanding, for the magnetometer should still be all right because it will still consider where is the north, the east, the west, and south. But I don't know for the accelerometer because then what was a positive value of Z, now it will be a negative to some extent. Is there any way to pick that automatically?
I don't think anybody's come up with a nice automatic process because you would need to look at something over time. There's ways of calibrating it on the fly that then say, right, my normal operational plane, which would, if you had a sphere, would sit somewhere, has all of a sudden shifted. It means that the whole collar has shifted. So you could take a whole day's worth of data and see where it sits in 3D space. But it doesn't say whether the animal is walking uphill or if the collar's like, oh, maybe not uphill is not the right thing, but say it's got shorter legs.
No, exactly. It's always.
If it's tilted in some way, with a lion, it's easier because the ground is usually perpendicular to gravity.
Yeah.
So if the whole thing shifts, it means that the tag has shifted and now it's not operating and it's at a different angle. And you have to do that with any animal, really, because however you attach the tag is very rarely completely parallel to gravity. So you have to tilt shift the whole thing. And you can do that through a day of recordings.
So you're actually identifying kind of the moment and then
the period of
adjusting.
time.
Yeah. Let's
say if the thing was running and the collar went ba-dumph, ba-dumph, you would see that as dynamic movement and probably not understand that it's tagged. That's very hard to get away from.
But if it stays for, I don't know, 2 hours, then I can adjust that because...
You expect that it's not running on its side for 2 hours. So you have to put those biological limitations. But the easiest way to do that is to visualize it in 3D space. If you put all three together, then you can see those patterns better.
I disagree. You can do PCA. It will rotate your axis.
So we have some tags on crowned eagles at the moment that's collecting ACC data every 2 minutes. It's an 8-second burst at 20 hertz. And we have no validation at the moment. And the tags are also, there are a few that are a bit different because they're tags that were donated to us. And I'm just thinking, is there a way that we can still use this data to make inferences? Is there a way to say, okay, this is roughly what golden eagles do? Can I use that as a bit of a reference point just to look at coarse behavioral types?
Definitely. If you 8-second burst, 20 hertz, it's quite a nice period of time. If you think about your GPS points, we're making a lot of inference about behavior for an instantaneous point and where that exists. You put 8 seconds around it with some information, it's definitely. It just depends whether you use thresholds in some way, or you can see a behavioral trace within those 8 seconds that tell you a little bit more about the motion and that use that to classify behavior.
Okay. And my second question is for one of our individuals. For a day, we actually put him on 5-second bursts. 5-second GPS locations. And you could nicely see the bits of thermal soaring that he was doing and circling back. And I was just wondering, what is the energetic trade-off for a particular unit to just do very high resolution GPS data versus all the IMU metrics?
That's a massive discussion. It all depends on how the chip records to memory and then how it sends the data back to you. You get more data, you can get more numbers if you go for IMU, but the power to retrieve that and send the data, it can be done in packages like you saw with the EOBs there, which can then really decrease it compared to what you do with how you save GPS data. It's a really big discussion, and I'm happy to have such a discussion, but always bring engineers into it as well, because they're the ones that fully understand how the memory and power system works. Yeah.